Okay, I just wanted to start this panel discussion from you, Tushar. So, Tushar, you've just delivered a very nice keynote presentation on AstroSim and more generally the hardware-software co-design opportunities for AI compute. Really loved your talk. It would be great to hear your perspective on actually what's happening with us seeing so many startups, specifically in the AI accelerator space. And this space, just for context, we know that it's a tough space to be in commercially. And yet, there appears to be quite a bit of activity there. And what drives this rise in the number of companies that are jumping into this space? What is it that, for example, the systems people are missing? And to follow up on that, is it specifically the hardware opportunities and hardware acceleration opportunities that they see for the purposes of running AI workloads, or is it also hardware software co-design opportunities there as well? So what's your take on that?
That's a great question, Alexey, and Stefanos for I just want to make sure I'm getting an echo. So
there is echo from our part. Maybe it's coming from the microphone, because we have to also have the microphone on the other side.
All right. So as long as you guys are able to hear me clearly, good. So Alex, question is coming from why so very much interest in AI, especially why so many startups. And I think I'll start with some of the key I think key trends or directions that have led to this. So fundamentally, right, like we, at least as as computer architects, we know that if you have a specific workload of interest and you design a specialized hardware or system for that, that gives you about, give or take 1000x better efficiency in terms of compute utilization, compute flops, and energy compared to, let's say, a conventional CPU. So this is something that people know. And, it's the challenge has always been that it does not make economic sense to go and build something customized, which is why, especially maybe for very, very specific use cases like, military and so on, people still build customized ASICs, though it's very expensive. And otherwise, you have to do with CPUs, great, or people just go with FPGA. So that's kind of been the trend so far. I think what happened with AI is that, again, massive compute demands, massive requirements for efficiency, and the fact that Moore's law kind of slowed down / ended, we can't just rely on CPUs to get us there. So I think given that and the massive demands and the economic, I think, opportunity, there has been a big trend towards designing custom systems, right? Custom systems includes both custom silicon chips and, of course, custom nodes and systems overall. So there is kind of the economic argument, and there is the, performance and energy efficiency argument. Now, what's very, very, and I think what's very interesting now is, if you think again from the co-design stack that I was talking about, fundamentally you're starting with some algorithm that you want to run, and, really at the bottom of the stack is the specific, hardware device that you're running it on. So if you can, and I think the biggest bang for the buck really comes from these two ends, right? So algorithmically, if I can just change the number of computations and memory accesses, that is obviously going to give me a lot of benefit, which is why there's, of course, a lot of work in the ML space, right, to make models more efficient. And on the hardware end, what the startups are going for is saying that if I can give you a device that fundamentally changes the cost, right? If the cost of doing each computation is cheaper or more efficient, and if the cost of moving data is again cheaper or more efficient, then that's where the biggest wins are. So I think that's the opportunity where I can fundamentally change the costs, and that will give me the biggest benefits. Hence, yes, a lot of interest in startups in this space, all the way from ones that are just designing custom hardware. It's still conventional digital logic, but custom hardware for AI, to people who are looking at new technologies, compute in memory. There's startups that are looking at photonics for compute. Then there's startups that are also looking at communication, again, conventional communication versus photonics and wafer scale and so on. I think so that's kind of the opportunity. But now I think to kind of come to the point you mentioned about the systems folks, I fundamentally feel that even if, I give you a piece of silicon or, a fabric, ultimately, you need to use it efficiently. Like otherwise it's not really beneficial. And I think that's where the systems opportunity is. And I feel like so we have a lot of, compute units now, we have a lot of memory units, we have a lot of fabric. So I think that's where the systems opportunities, that's where all the co-design opportunities, right? Like how do I utilize these systems most efficiently? And that's one angle. How do I utilize these efficiently? And I think the second angle, which I know some of the other panelists have been working on quite actively, is ease of deployment. So it's not just about making things efficient, it's also about making things deployable very easily, so that if tomorrow I have a new model up there on Hugging Face, it is push button for me to just immediately be able to deploy it. So I think those are the two angles where there's a lot of systems opportunity while we have new hardware and new systems coming up.
That's great to hear. Say, do you have a counter argument coming from the industry? Is there something that we may be missing in an academic setting that you get to see firsthand from the standpoint of commercial activity in the domain?
Yeah, so I mean, I don't think there's anything that people in academia are missing, right? So many of the startup, I mean, they're started by people, right, who are coming from academia, right? So yeah, so definitely agree with Tushar on, so on his point. So I think one thing that's actually interesting here is it's going to involve a co-design of not only the system and also the hardware, but also the algorithm itself. Right, so I think that's a really interesting part, right? You can start to change the model architecture, you can start to change the algorithm actually to fit your hardware, right? So that probably contribute a little bit to the diversity we see in all those companies, right? So that's probably why there are so many, right? Because really there are so many things that you can actually do depending on the view you are taking about the fundamental instructions that you want to implement. You can actually build a whole startup out of that, right? So I think at the end of the day, I think the market will figure out essentially what makes sense, right? So, and also I think, it's kind of really exciting time, right? So I think it's kind of a good thing that there are so many different companies, and many of the idea, if not all of the idea, are kind of coming from academia. So I don't think there's anything missing from our side, right? Yeah.
Great.
If I can add some comment.
Yes, please.
Maybe I feel like the trade-off space is really huge, especially with respect to certain metrics. And so I think that what's interesting is this co-design. It's not just may need to consider kind of algorithms, hardware, but also deployment context, because in different deployment contexts, whether you're thinking kind of data center versus edge versus scenarios where you have maybe privacy concerns that dominate the trade-offs that you may need to design around may be very different. So and the gain opportunity may be huge. So that's why it's important.
That's a great remark. And actually, these trade-offs that manifest in different points of deployment may not necessarily, may have, let's say, a common denominator. So an example of this could be from the cloud or the data center's perspective, when you have enough compute, the main bottleneck, as Seth said, is network, so traffic. However, on the edge side, you see this network traffic being the bottleneck between off-chip and on-chip memory. Dan, would you like to talk a bit more about that? Because I know that your work in compression really tackles that explicit problem in the edge domain.
Yeah, so I mean, maybe to start from a higher level view, I think we may also be expecting a bit too much from the current state of the market, because I think it's been literally around a year since some of these first models have taken off, and it's certainly not enough time for hardware to consolidate. I mean, there have been, of course, startups looking at slightly different setups for deploying these types of models. But I think it's also, we have to give people time to sort of adjust to their systems, hardware and software to the new market realities that are still sort of, models are still being, like, state-of-the-art models are being released almost weekly and so on. So I think we have to just be a bit patient with respect to this. And there will be consolidation for the better or for the worse. From this point of view, like from the point, just answering your question more precisely, I think it's really exciting that we are at the point in time where you can, I mean, in some sense, the way things are being run, the way the algorithms work, you can actually run fairly large models on end devices, which I think would not have been the case, for instance, for vision, because there was just too much compute and sort of too much memory in the sort of necessary for the activations. So I think it's so this is sort of where my lab has been sort of active in trying to understand what is the minimal amount of memory that you kind of need. And fortunately, we're kind of fortunate enough that the compute is sort of where you're doing autoregressive inference is not that large, so you could actually reasonably do this on an end device. However, I think we will also need to adjust to market realities. So I think people are going to move to sort of batched versions. Like probably the algorithms are going to change, which means that people will actually have to go back to sort of more stable state in terms of the trade-off between memory and compute. So probably, I think a lot of this is coming from the cloud side, where my guess is some people are unhappy about low levels of utilization and so on. So I think it's an extremely exciting time from this point of view. Things are moving a bit too fast because your assumptions can change from week to week, but certainly very exciting.
Great. I like really much how you pointed out that we're really into the year, but a lot has happened if we think about where we started.
I know it seems a lot more. Yes, it does seem a lot more to my students.
So, should we talk at this point about co-design, or is it like Intel's life cycle? If you remember several years back, where there was the tick and the tock cycle, and first you have like the algorithmic. Oh no. First, let's say that you start with the hardware that enables certain workloads, and then you need to develop your algorithms in order to be able to catch up with to be able to run it at scale and at cost, and then you iterate on the next gen of hardware, be it on the data center or like on the edge. I would like to hear your thoughts. Whoever wants to go first.
Yeah, I can chime in a little bit of that. I think that's a great question, right? And I mean, this is something I know since a lot of my work is on the hardware side. Hardware designers are struggling with. So I think Dan made a great point. Like somehow in this AI space, things are moving so quickly that things that were 1 year ago just seem like, oh my God, that was so ancient. But that's not the case, right? I mean, it is. So that's actually been a challenge for hardware because it takes time to develop hardware. It is, how much co-design should you do? A new fancy model comes out, like, should you just invest? And I think like there's examples of this. I remember like, maybe again, even though it's like not that far behind, but I remember LSTMs and RNNs were extremely popular, right? And in the architecture community, we just had a suite of accelerators optimized for LSTMs. They were going to be the next big thing, and they were for a while. But and then transformers came, right? And so if I'm a hardware company, whether I'm a big company like an Intel, IBM, NVIDIA, AMD, or if I'm a startup, should I start investing in hardware support for some of these blocks? And what happens if those don't pan out? How should you handle kind of programmability, flexibility, and handle these changes? I think this is an open challenge today, and this is something that people do struggle with on the hardware side, because once you bake something into silicon, it is going to be extremely challenging. And I was listening to a keynote from Google where they talked about how they made some, maybe, especially I feel like for a company like Google, where they are actually also investing in algorithms, they mentioned how they made some calculated bets on certain, modules that will pan out, and maybe they did, right? So they said they kind of proactively, when they publicly announced that they had proactively put in a sparse score, and now, that is actually being used quite actively. But it is certainly a big challenge. And I think that TikTok model, which worked well earlier with slow cycles, is something that, at least in the AI space, is much more challenging. Yeah, and I don't have a clear solution for that. I think my general 2 cents here is that what is definitely needed and valuable is the fact that you can have hardware that is still very programmable and agile as software moves or models move, which is, I would say, also the reason why let's say a company like Nvidia has been very successful, right? Like they have a very programmable engine. So versus, I would argue that there are some startups, if you just look at the raw hardware, the specs, the microarchitecture, it is definitely a lot more optimized, and it'll probably give you orders of magnitude more speed up for that operator, let's say, on that hardware, as opposed to a GPU. But if you look at this full workload and you need to program it, then the benefits don't seem as much. So one way of thinking about it very concretely is, this is where Amdahl's law comes in, right? So again, if let's say 90% of my workload is all of these AI ML operators, and while 10% is just other entities, the maximum, even if that 90% gets is something that I can like reduce the compute time for that to 0, the maximum speed up will be 10x, right? So I think those are things which people are kind of realizing and struggling with. And it is, again, an exciting and open question in the hardware side on how do you do co-design for things that are evolving and while still making things programmable. Yeah.
Actually, this is a great point, Tushar. I was just kind of waiting for my turn to raise this question, I guess, to the panel. Is there too much appetite for specializing things right now? Because I think maybe people have forgotten history from the previous century, when there was quite a bit of design actually happening on the CPU side of things. And until it acquiesced into something that was actually generally applicable for a broad variety of workloads. I'm wondering, and I'm concerned for all these startups, actually, that they might be going through the same phase. And as Dan pointed out, maybe we are simply waiting for the market correction or a market consolidation event, right? Because it's possible that some of the researchers are super excited about optimizing some specific type of operator, and they can get orders of magnitude performance improvement. But how general is that? Do we need sort of this differentiation in terms of AI accelerators for inference versus AI accelerators for training? Is that difference at that granularity fundamental? I think the jury is still out on that. I mean, we do see the market, and of course NVIDIA in particular, and other players like AMD producing GPUs that are specialized for inference versus training. But how fundamental is that difference is unclear. And even further, some AI accelerators are being developed for specific types of neural network architecture. Maybe that is taking it a little bit too far.
Yeah, so I just wanted to comment a bit on this kind of at the intersection of the last 2 points, because it would be very nice if things were working in this kind of regular cycle, sort of algorithm, sort of software, hardware, and which would give people a bit of room for breathing. But I think the cycle has accelerated so much on the algorithm side, at least, and that it's really. I think there was a nice way of phrasing this by Sarah Hooker. It's become like a lottery from the point of view of the hardware. So it's literally like you just hope you're going to come out at the right time with the right accelerator that hits essentially whatever is popular then. And we can see some startups have, some hardware startups are successful. They won the lottery, and some of them unfortunately have not. So I think this is. I think it's going to be quite a bit of time before it actually gets back to the regular cycle, if it ever comes back.
Yeah, so I totally agree, right? So I think we are in the phase that like the algorithm modeling innovation is kind of so much that very hard to build hardware, right? So and like the algorithm side, for example, like for speculative decoding, right? So I don't think the community is passionate too much about it like 1 year ago, right? So I think GPTQ, I don't think is more than 1 year old, right? So like all of the things that, so essentially right now it's like we don't really know how far we can push for it, right? So I think part of part of the pace of innovation on the algorithm side is we are really excited about the potential, right? So like if you say, okay, we are happy with what we are right now, then we can start to build hardware. But I think the feeling from the algorithm model side is there are probably way more to squeeze on algorithm model than the hardware side, right? So I think the consequence of that is we look at the granularity of the instruction, right? So I mean, the layer of matrix multiplication, I think that's pretty much settled, right? Everything is just that. But another step to reach the level of abstraction to say, okay, let's have a transformer layer, right? As a one key instruction. What that looks like, I don't think that's even clear, right? But I guess the good thing about having so many startups is hopefully one of them will win, right? And then we have something great in the end.
If I can add to that, I actually think it's dangerous right now to think about, oh, things are moving too fast. Let's not co-design. Let's wait for things to stabilize. I mean, there's so many valuable lessons learned from this process that, you know, if we ever do stabilize, hopefully we'll have a toolbox of fantastic techniques that will go into something that will be, you know, a general purpose AI inference and training all models instruction set or something like that. But you know, right now the sort of the costs involved on both the training and the inference side and the pre-processing side are huge in terms of just sort of basic resources, energy, sustainability, all aspects, right? And so not to try to address that via co-design and not to try to look for those solutions, it's dangerous. I do think that part of what we're seeing is a function of the fact that some of the infrastructure for hardware design has also progressed, right? And that makes it possible for this kind of innovation to happen at the hardware side. But just to say, you know, things will change. Let's just try to make things work with the, you know, with the GPUs. It's leaving a lot on the table.
Yeah, these are all very insightful comments. However, I would like to point the difference between the cloud world and the mobile world or the edge world, where you don't really have either the area or the thermal capacity or even the budget in terms of compute to have general purpose hardware for everything. So how do you think the world will shape towards that part of the spectrum?
I mean, I think I would actually be curious about to hear from some of the panelists, because it's not completely obvious that sort of people will be able to run this on the edge, like some of these models on the edge. I'm hoping certainly that this is going to be the case. But if you want to run like something of the quality of GPT-4 on your phone, I think maybe we need a couple of hardware generations and quite a few innovations to sort of be able to do this without your phone melting down or whatever, and we're turning into a laptop. So I'm kind of curious but I think kind of API access might actually just be the solution for this, and we'll have a very good connectivity, very low, like high bandwidth and low latency to APIs, and maybe they will drive things. I'm sort of curious to see what the other people would say here, because that would actually turn it all towards the cloud, right? And then you have maximum opportunity to batch, and you'd have maximum utilization of your accelerator, and that everything would be fine. So is that something that you think is going to happen, or do you think it's going to sort of run
The thing is, at the end of the day, it's still somebody else's computer, right? So for privacy reasons, you might want to run certain workloads on premises, be it on your device or certain like closer to the edge device, not necessarily.
I certainly hope that's going to be the case, but if it's technologically impossible, I mean, I wouldn't have expected everyone's email would be with Google, or 90% of email would be with Google in 2023. But I do think this is pretty much a reality, right? So, yeah. Anyway, I think it depends. It really depends. But yeah, this also makes me uncomfortable. I completely agree. It would be nice if there were a way forward where people could actually run everything on personal devices.
So I think wearing the hat again of like, what is feasible from a technology perspective, I think it also ties down to the discussion we were having just earlier, right? On whether there should be a, convergence or whether we should still optimize. I feel like, so there is certainly a difference in cloud versus edge from that perspective. Like cloud is really meant to be, very general, like, a lot of different use cases, multiple people running different kinds of models. And that's where I think there is hesitation on, baking some things too specifically into silicon. While on the edge, and maybe even kind of still that lottery argument Dan had, but people are, willing to take bigger bets, right? Like, I mean, on the edge, if as an example is, I have, let's say, an AR VR device, and I kind of know exactly the kinds of models I'll run there. Yes, we're still innovating in that space. But there is an appetite for really, really, doing heavy co-design to the level where that engine is not going to be programmable at all, and it's only going to run a subset of things. And also the fact that we've again reached a point where people are a lot more comfortable in replacing edge devices, quite frequently, like 6 months a year. And so, so there's volume there. So which is why I think there's a lot more co-design, specialized solutions, and even startups, I would say, that are focusing a lot more on the edge. So I think to Dan's question, I think, yeah, it's still an open question on how much will be feasible, but I feel like there are some orders of magnitude you can get by that heavy co-design, like technology and, integration and device and so on. Now, and beyond that, there are all of the algorithmic optimizations that, again, some of you, Dan's work on, like, sparsity and some of the work people are doing on heavy quantization, even like some of the work I know Alexey's group does on trying to make sure, things are just, there's a lot more sharing you can get. You have some larger models on the cloud, but, fine-tuned models that are deployed. I think there are interesting use cases that might still allow things to be deployed on the edge. Maybe there will be, of course, naturally some trade-offs of accuracy versus, versus performance. But I think given even the privacy arguments, yeah, I feel like there will be some very specific on-device run use cases as well. And that's where I think a lot of that heavy co-design will help.
Yeah, and if we think about that sort of device edge, I mean, there is a history there that ecosystem has just worked around specialization. I mean, there's so much custom accelerators, whether you look at smartphone segment or automotive segment or, sort of infrastructure, the process of integrating special accelerators, it has been more established, more accepted. The impact on the entire stack has been also, it's worked like that for a while. So there, I'm less worried about if there is an opportunity from a certain accelerator, whether the path to market exists. But I do think that kind of Dan's point, that there'll be certain things that that we can do when it comes to the AI algorithms that just are not feasible on the edge. And so it will be important to find solutions where we can leverage both or find ways to leverage both bigger models that are supported by cloud and still allow some type of computation, some type of AI to still happen at the edge, to kind of be able to work across the continuum.
Yeah, so I think totally agree, right? So so I feel like another angle is, do we really need to run GPT-4 style model locally, right? So I think one of the key things really about the model capacity, essentially, do we really need to run large model? So if you look in the next 10 years, right? So 10 years, who knows, right? I mean, so next couple of years, right? So will the model keep getting larger, or will the leading model keep getting, start to get smaller, right? Because we are right now in this exploration phase that we don't really know what to do. We'll keep adding data. But I guess one question is, how much of it is really necessary to actually make it work? Right, so I can probably see a world where the whole thing start to get smaller. So especially when you start to work on very specialized tasks like summarization of email, right, retrieval of your personal thing, right, for all those privacy related subtasks, maybe there is actually a very small model can just get the whole thing done. Maybe we can start to decouple the model architecture in the sense that the fundamental knowledge of English are stored essentially on the cloud, and then the personal component is actually stored on the local device, right? Maybe you start to have the coordination between this cloud and edge. Maybe the model is just small enough. I mean, the whole Wikipedia is not that large, right? If you really start to compress it, right? So maybe you can have a small model, couple billion parameter model that really comfortably fit into the edge device. And if you want to do some crazy task, maybe you still go to the cloud. I wouldn't be surprised if that's the future, but yeah, so super excited to see what's going to happen in the next couple of years.
I'm kind of hoping that's the future, to be honest. So
yeah, so I'm kind of optimistic that's the future. I don't know why I'm being optimistic. I feel there's nothing stop us from making that the future, right? Because there's always search engine, right? So when you do not have knowledge, you can always search. And then all you need is this basic knowledge about the world, which probably Wikipedia, right? And then you have different language capacity, you know some basic task. Maybe the architecture start to evolve in that way.
I mean, historically, in all other contexts, we've aimed to find ways how to do more with less. So why not here as well, right?
Yeah, exactly. Yeah, so I think that's why there's always a GPU rich and GPU poor type of argument. I mean, being resource constrained might not be a bad thing. That will probably force us to actually think in a more principled way what is really fundamentally necessary and what is something we can get by just Google it, right?
Yeah. I agree with the asterisk of multimodality. So right now we're just talking about text, maybe text and image. When we span to video, then all bets are off, I guess, in terms of the architecture at least. And the second pillar, which is the other side of the coin, is the pursuit of AGI. I don't know if it's a marketing thing or we're actually pursuing that in essence, but that seems to be the end of the tunnel at the moment. So how do you feel about that and the previous round of discussion on we don't need to run everything or we don't need to scale up the requirements up to the maximum?
I mean, I get it that adding video to the mix will push the complexity and resource requirements of training process, model sizes, and everything. I still think that sort of the statement, ultimately what we want is to end up with smaller models that may be useful in specific context, and to put emphasis on how do we build these smaller models, how do we make it possible to identify the kind of model context match and look for efficiency that way. I think that's orthogonal as a goal. That's orthogonal to the goal of being able to train with or work with video content and these more challenging and resource demanding types of pipelines.
Yeah, so we discussed these sort of two extremes, whether or not we want to specialize for running in the cloud and what specialization means for running on the edge. And I actually agree with the panel wholeheartedly that the edge actually drives most of the use cases for specialization. And this is where, it's going to be happening. And I also really like the future where we are much more power and energy conscious in our AI design, because, our friends from the AI community this is not their primary concern, but that's why we're here, to help them out with that. But let's talk about something that's maybe less than 10 years from now, right? Let's talk about, with this advent of large language models, everyone driving a Tesla would want to have a large language model on their autopilot, so that they can give them commands instead of pressing the buttons and being distracted from the traffic, right? And sort of orthogonally to that, there's also a sliver of the community that consists of very senior systems people who believe that everything should run in the cloud, and to the extent possible, they want to move as much of the workload to the cloud. So maybe there's a happy medium of where we can actually run things in a hybrid fashion, right? Can we run something on the edge cloud, essentially? Can we run that large language model or offload some parts of that computation on the AV, while also offloading some of that to the cloud as well? And large language models, in some sense, they are probably at the forefront of pushing against the resource restrictions and the power budget and the energy budget that you have at your fingertips on the cyber physical systems like autonomous vehicles. And they believe that this can happen in a soft real-time fashion, meaning that whatever you have to do is in a tight control loop, is latency sensitive, it has deadlines, and it's a soft real-time system. So just wanted to hear the panel's thoughts on the feasibility of running such latency sensitive applications on the edge cloud, instead of either on the edge or on the cloud.
So this is actually a great question, Alex, and I think this, especially in the context of something like autonomous vehicles, think it comes also to, I remember one of the points Alistarh talked about metrics, right? So from a systems perspective, a lot of times we are optimizing for, averages, right? So, on average, this is, number of tokens per second or whatever, right? Or number of inferences per second, this is the throughput. But in a system like this, it's really like we need to have bounds on the worst case, right? Where this is, and I know, for example, if you think about how, chips or systems are built for, let's say, aeroplanes today, right? Like they actually have a lot of redundancy built in. And I remember even from the context of, again, computer architecture, where there's a lot of, things and techniques out there for optimization, speculation, and so on, where it makes sure that, on average, you get better performance. But there could be, if misspeculation, there could be very worse, adversarial scenarios. And I know that whenever I've spoken to folks who work on like more real-time systems, they talk about how, they will not, allow two cores to talk to each other, because there's going to be through memory, there's going to be, some, weird delays there that they can't account for. So they have a lot of mechanisms built in for determinism. And I think, so I was just saying that I think once we start thinking about use cases so there's a difference between listening to, playing a game on your phone where worst case, things are delayed, it's fine, versus an autonomous vehicle. And I feel like one is, I think, design for the worst case will become challenging. And now whether that can be handled purely on the edge, which, yes, if it's purely inside the car, it makes sense. Things might be more deterministic as opposed to the cloud. But I also do feel and agree that, especially a lot of the works that you guys have done on, systems and networking and interaction with the cloud, it might be possible to still provide certain, guarantees. And I think, I feel like what might end up happening is, Alex, you kind of, I think, mentioned this notion of hybrid. And I think Dan had this point about APIs that stuck with me. I feel like ultimately there will be interaction with the cloud via these APIs. The question really is, when do you do this? Maybe there's very latency critical tasks for which you want to have, just everything running on that device itself inside the car. Else you might have, some slack to go to the cloud. I think the open question on whether there's going to be some middleware tiers like an edge cloud and edge infrastructure, some smart city like infrastructure that is really just hosting these services as opposed to the cloud, which is again everybody accessing from everywhere. I think those are some interesting open questions that we as a community will need to think about.
Yeah, I would. I think that car is an easy example, actually. I mean, I have a huge amount of space in the back, huge amount of space in the front. I can put so much compute, so much storage. But car is not where we should be looking for the really pressing examples. Drones may already, kind of start posing some stricter requirements, but cars should be. I think that we can do a lot in a car, and that's not where we'll find the biggest constraints. One thing that other than these sort of performance and tail performance type of trade-offs with respect to resource footprint, the other dimension that I think is going to color kind of what the design space looks like is going to be privacy, whether it's sort of a personal option or regulatory privacy. I get it that yes, 90% of users of email is in some Google data center, but there are more regulations now, especially in certain spaces on where that data can go and should go, and whether you can make some guarantees as to how that data sort of tainted the rest of the system. So relying purely on software techniques to make those guarantees may bring everything else to a standstill. And so that's where I think maybe some opportunities for co-design are going to exist.
Great. Can I go back a bit and ask about optimizing for the average case? And I want to correlate that with evaluations in general in these new models. So Tse actually said that it's problematic right now. It's not a solved problem. It's not automatic. And we may have blind spots. So from the standpoint of, let's take quantization, for instance. Let's say we're quantizing a backbone model. How do we assess the average case, and how critical is the long tail of the distribution? Dan, maybe.
I feel like I should answer this one. So I think I'm not quite sure exactly whether you're referring to performance as a function of accuracy, like model accuracy, or whether it's a function of model like raw throughput. I think the most, maybe perhaps the more interesting question is actually about model accuracy, because this is where I think a lot of the like sort of new results have come out over the past couple of months. Because I think sort of in the first round of results on compression of these models has come pretty much in the second half of last year. And I think we literally had to sort of brew our own evaluations. I think we made some good choices and maybe some bad ones as well. But I think people basically measured distributional match, so by perplexity for large language models. And also for vision, for instance, people usually go by top one accuracy. But that doesn't tell you the whole story, because you can look at like performance across subtasks. Like, for instance, you could look at sort of poorly represented samples in an image domain, let's say people of sort of different races, and or you can look at different types of tasks for a language model. For instance, reasoning tasks are known to be much harder than sort of the average guess the next word type of question. So then I think where people are looking a lot, sort of are digging really deep these days, is it does seem like there is this kind of tail distribution with respect to performance across these harder tasks. Like in particular, compression is worse. Like, it does lead to worse performance on harder tasks. But at the same time, this is where Google and Microsoft and OpenAI, they're spending most of their compute because they want to get AGI. They don't want to, just write sort of rhyming essays or something like that. So the point, I think this is where there's actually, I think it just opened. Like how much is actually lost, how much is just poor calibration of the model because of compression, and how do we recover? That's also quite an open question. I mean, we're working on this, and I'm sure other groups are working on this as well. But it's a very interesting area. We know very little about this, I think. I mean, maybe the one thing I'll mention, because it says around, is I think there's a huge need for good sort of evaluation gauntlets that can run fast, be distributed well, and are sort of widely accessible. They've done a lot for this, but I think more can be done towards this, because I don't think the community has come to a standard, to an agreement. Even this kind of recent Gemini, this recent Gemini launch showed, people will still evaluate the same thing in many different ways and come to different conclusions. So,
yeah. So I think evaluation is a really big problem, right? So we see how people deploy those models. I think for each individual company or customer, I think the evaluation is more clear because they can always do A/B testing, right? So all the old software practice, they still apply, right? So we see people just like partition the input stream into multiple models and ask, and then essentially do the old CI/CD style or kind of continuous integration style thing when the new model comes in. I think for this case, it's kind of more clear what to do. I mean, there's still challenges, but I think at least people know where to start. But for really comparing the capacity of the model in general without knowing what you are going to do with it, it's a very big challenge, right? So downside, right? So essentially, well, given how much financial incentive it is to have the best model, right? So I mean, people will just essentially we need a good standard from the community about, how should we even talk about capacity of the model, right? So I mean, not to say which model is the best, but really try to understand the limitation of the capacity, which part of the capacity that this model does well than the other model, right? And then we know where to improve, right? So I think that part is largely missing. So we have been run all the open model for Helm, but but definitely need more. So essentially community to kind of converge on a set of tasks that we believe is kind of measure the capacity in a diverse way, and have an automatic way to, or semi-automatic way to say, so this is actually how to measure your answer is good or not, right? So,
Great, thank you. One more question from my standpoint is that there used to be the argument for federated learning that you get access to the long tail of data that you normally cannot centralize. But nowadays it seems that we're crawling everything anyways, and we're centralizing everything. Is there space for federated learning nowadays in the era of LLMs?
So I think maybe I'll answer this, because I would like to maybe challenge a bit this kind of, I mean, of course, companies will crawl a lot. And I'm not sure how much Zhang can tell us about this, but I would be curious to find out as much as possible, as much as publicly, as much as what can be stated publicly about this. But certainly, I do think these companies, especially after companies like Google and Microsoft, after Meta after billions in EU fines, I do think it's no longer the Wild West with respect to what they can crawl. So, for instance, if you would like to have, let's say, an email assistant in Gmail, you're going to have to probably build your own or go with some other company, because I am afraid Google will not be able to train legally on your email data or something like that. And I'm not sure they're planning to do anything of that type. So My point is, I think by now there are some guardrails in place, especially if you're in Europe. And I think this actually poses a really quite interesting question. And one phenomenon I'm quite interested in are these kind of adapter exchanges where people will train on local data and essentially post essentially digests of models online, and you can take them and merge them. You can sort of study them if you want. Some of them leak data, some of them do not. But I think it's kind of a fascinating instance of manual federated learning, where essentially like everyone posts their updates to, let's say they started from Llama, they sort of post this, and then they start to actually, you can manually merge, and sometimes data merges cleanly and sometimes it does not. Sometimes it results in improvement, sometimes it does not. I think this is quite a fascinating area, to be honest. I'm very happy to sort of hear what the other panelists have to say on this topic.
Yeah, so I think, so I'm speaking as a professor, right? So I think really one thing that's really exciting for the field is really try to understand what is the economics of the mechanism of getting data legally into the language model. I mean, so legally is one thing, but another thing is having something that's acceptable from the society, right? So I think right now it's like, I mean, there's common crawl, right? So and the common crawl is out there. You can always process common crawl, right? So there's a whole bunch of open data set that people just put out. But I think in a longer term, there need to be this data framework that both parties are happy about, right? The data consumer and data producer, they are okay with this specific way of exchanging data between human and model. So I think that's really a fascinating research area, and probably something that the academia has a lot to do to really set up essentially the right conversation, set up the right proposal. So I think that's something that need to happen, right? So I don't know how, but I think it's really, really important problem, for the sustainable growth of the area.
Yeah, and this is why I mentioned the sort of the privacy issue, from kind of from a cryptographer's point of view. This is possible, right? They have a number of techniques that make it possible to make strong guarantees regarding data privacy, to compute over data without revealing it. It's just from a practical perspective, we're very far from being able to just adopt those kinds of techniques. There's tremendous progress that's in the order of 1000x improvements, right? Given how far behind that field is, but we need another 1000x before this probably becomes acceptable on some scales that are relevant, and then in the meantime, thinking about what else one can do at the system level in terms of making guarantees, or at least just being able to kind of do the audit part of how data is used, like even if it's not the guarantees on isolating data usage, but just the auditing part. I think that we still have a lot to go.
Yeah, actually, I think that Dan and Zhang brought up a very good point about the economics and the economic mechanisms. You want to make sure that, to me, and not just to me, but I mean, a lot of people spoke out about this, that data is the new oil, essentially. And just like oil, you need to refine it, right? You need to have the entire pipeline to bring it into the consumer's hands, right? And the question is, what is that pipeline for the machine learning world? How do we create a marketplace where we basically perform a distillation on some privacy-sensitive data, but in a way that is privacy-preserving? how do we expose that into some sort of marketplace, and then how do we measure the goodness of those models? And this is what Zhang actually said earlier. We need some sort of standardized benchmarks that sort of extend way beyond ImageNet and those isolated tasks that we currently have that measure the goodness of the model. And the model could then sort of expose its capabilities declaratively. So, and you can write the applications on as an application developer interacting with this marketplace or participating in this marketplace and consuming the capabilities of the data. So I think that's just a fascinating future that sort of calls for economic mechanisms that are incentive compatible.
I think we lost
the audio from their end.
Yeah.
What's happening?
We lost you for
you lost us for a bit, right?
Oh, did you?
yeah.
Maybe you can repeat
The whole
summary?
thing?
No. Maybe a short summary of it.
Yeah. Basically, I was saying that the economics of making sure that you distill the data in a privacy-preserving fashion into a marketplace and make it available to the application developers is really interesting. And I think that's the future because data is the new oil, and you want to be able to find standardized ways to refine it, and ways to sort of come up with incentive-compatible and strategy-proof economic mechanisms that allow both the application developers, which are the data consumers, actually they're the model consumers, and the data providers, the data producers, to participate in this marketplace.
Yeah, I love the analogy. This makes sense. Yeah.
Time we can move on to the Q&A with the panel session. So while other people are preparing their questions, we already have one from the audience, and this question is directed at Dan. The first question is what issues are you facing when you move theoretical optimization algorithms into practice?
I could probably give a whole talk on that, but I think one issue is, some assumptions are no functions are smooth and strongly convex in practice, except for quadratics. Those are not that interesting. I think one thing that seems to be very clear is, for instance, like everything you come up with, if you want it to be practical, it has to be vectorizable. So, for instance, I realized alarmingly that 4 out of my 5 PhD students are actually sort of GPU programming experts by now, even though this is not what I sold them into when coming in. So I think, I think one has to have good hands these days if one wants to have impact. And I think, for instance, TreeDAO, it says collaborator is an excellent example of this. As someone who has very, very good in systems insights and algorithmic insights, but also is able to put them into practice. And I think that's really the difference between having a small amount of impact, or like coming up with a beautiful result, and actually having your code be run by hundreds of enterprises and like pretty much everyone on the internet. So yeah.
Great, thank you. The second question is, what is the role of theory in practice? How important is to ensure certain guarantees in practice? I don't know. I think it might still be to Dan or to everybody actually.
I mean, I think that I also should probably have a pretty good or maybe a better intuition here, but I think I think a lot of this, a lot of the art of being a good advisor is to actually find the right set of constraints for the students to work under. So I think I've been lucky on a couple of occasions to find out some, like essentially have like an algorithm that worked under the right set of assumptions, which happened to be practical. I would have to admit that was more a chance than design. But I think other people seem to be doing this extremely consistently. Again, Chris Ray, for instance, is an incredibly successful example of this. So just follow the masters and see how they do it. But I don't know exactly how to answer this. It's just also a matter of luck, I would suppose. But yeah, I guess talking to people is always a great idea. Like talking to hardware people, talking to sort of good software engineers, I think is always a great way of bridging this gap.
Yeah, so I think one thing that could be useful is really talk to like the end user of the technology, right? People who are struggling about the problem, right? So I think that's one place I think industry and academia, if they work together, talk to each other frequently, can actually inspire each other, right? So many of the impact part really coming from, and if you want to discover them early, you probably need to talk to a whole bunch of people who actually try to extract value from technology but stuck, right? So I think that's probably one way to sneak peek into the future about what is an important problem, right? So yeah.
Do we have any additional questions from the audience? Yeah.
There's a question. Oh, you have a. He has a microphone.
I'm Reza Asadi from Tumin. Actually, I have a question about co-design, especially when you're thinking about edge environments. Do you think it's possible, or maybe it's a good idea to have maybe several specialized models for some tasks that giving us a desirable accuracy while meeting different other performance metrics like latency or throughput or energy efficiency and so on? Do you think it's a good idea to work on such kind of architectures? And maybe a related question would be that, okay, we have these large transformer-based models with a very high accuracy. But do we really need, or is there any path to maybe use another architecture when we are serving certain tasks? Thank you.
Did you hear the questions, guys?
Yeah, was the question audible for you, or do you?
All right, so let me try to summarize it a bit. So the first question was about co-design and whether you believe that we should have some pre-cooked or pre-trained models that serve as backbones and guarantee certain levels of accuracy or performance. Components.
We definitely don't have that accuracy that those large models have, but maybe can perform as good as possible on smaller subtasks. Each of them maybe special subtasks.
Right. So the question is whether we can have certain smaller models that can perform quite well in subtasks instead of having like the whole shebang. Maybe in relation to this, we can talk also about how having a really large model boosts performance on tangential tasks. I don't know who wants to tackle this first.
Yeah, personally, I'm very optimistic that on a specific task, small model should be pretty good. Yeah, so I think just like digging deep like into that, I think it's really is really the future. Yeah, like also related to the edge versus the cloud thing, right? So I think once we figure that out, right, the edge versus the cloud, the economics should be pretty, like at least much kind of clear about where the trade-off, where the cutting point is. Right? Yeah.
Yeah, just to add to what Say said, I think that I mean, I think that would be ideal. Actually, what the person who asked the question said, right? Where then in practice we could just have this very large. I mean, today, like I mean, GPT-3, ChatGPT. I mean, kind of is the answer for everything, right? But as we said, we if you want to deploy something on an edge device with a constrained set of tasks, then ideally we shouldn't have to deploy like the full-fledged model. And it's not just about take the full model and just compress it or quantize it, but really, like, I think being able to have certain tasks. And I think that's where I think some of the things that the panelists mentioned around some general kind of information about parsing what you said. I mean, there's some basic functionality you need about being able to parse whatever you asked but then being able to kind of get the specific answer. And I know things like there's a lot of talk these days about like RAGs, right? Retrieval augmented generative AI, where I think some of these ideas are things people are thinking about, where like the actual knowledge is kind of in some larger database and the smaller models to kind of retrieve. I think maybe techniques like this might allow us to get to that kind of a vision. So I'm quite curious and optimistic. Again, I don't directly work in the algorithm space, but I've been following that too, because it seems very promising from a systems perspective because then we really have to think about like designing databases for the kind of the knowledge part, and then some mechanisms for just the queries. So it's an interesting space that I'm very curious about.
Maybe a subsequent question to that is, okay, one take is that we don't use the same models and we just use different smaller variants. Do you see there is space that we can either super compress everything, hyper compress everything, or alternatively and more promisingly, whether we can have stochastic architectures that don't necessarily run through the whole network, but they only run paths of it in order to get certain result. Mixture of experts is one variant of it. Early exit models is a different variant of it. Do you see these being still relevant in this case? Thanks.
Yeah, so I mean, I think to some extent, mixture of experts are already running what you described. I think I think they had a paper called Déjà Vu, which actually runs kind of a dynamic mixture of experts of sorts. So I think certainly there's sort of I think there's kind of a lot of momentum behind this direction. I think the one thing that we've been looking at is more connected to the first thing that you kind of suggested. So imagine you have GPT-4, which is good at everything, but it's really expensive to do. So do you want to find a sort of a sliced up, like a really specialized version of it that's very good for some local data you have or some specific task, and throws away a lot of the sort of computation that you would not need, or also the memory, the weights that you don't need for, I don't know, there's a lot of information in there that you probably don't need. And I think, I mean, this sounds nice and elegant, but I think right now it sort of runs into issues of like practical issues. Like I know our optimizers are not really well designed to sort of like train over models that are really Swiss cheese. And like you can get really sort of a collapse. There's also like neurons usually are like superimposed features. That's kind of what happens during training. So it's very hard to affect by performance on like literally the same neuron could fire for completely different things, like completely orthogonal things. So it's really hard to remove just a certain type of information from a layer from a neuron without affecting its performance on other things that you might actually care about. So I think all of these are very interesting, but I think one has to be very careful with how with implementation. Yeah, but I mean, maybe one thing I want to mention is that I mean, small models are actually still state of the art for specific tasks. I think, like for instance, if you look at the classic benchmarks like Glue or Squad, actually the best models that I'm aware of are still kind of Roberta, like essentially large BERT type models. So the thing is, like, I think these still have they're no longer that sort of fancy, but I think people still deploy these if they want sentiment classification or like very basic tasks. So I think that's going to stay around for a while just because of cost.
So I apologize, but I'm going to have to drop off. When we're in an online format, you sort of assume zero latency, context switch time. So I apologize.
No worries. Thank you. Thank you for.
Thank you so much for inviting me. Thanks for chatting with all of you. Bye-bye.
We have one more question from the audience, and then we can conclude with one question about like what you're very excited about in the near future, either from work that you see or like from the general ecosystem. So what is the last question from the audience? Yes.
Thank you. I have a question. So there is a reality. So in the reality, there are companies that apply machine learning, but there is a limit. Like the companies may say, we will not say which task will be solved. There is this thing like Kaggle, and like a Kaggle, I don't have statistics about how much competitions, but like a couple years ago, like 3 years ago, the most prevalent model was just classical predictors with increase. So I'm curious, what's the relation between Kaggle and getting in general? Is Kaggle considered as a good proxy for real machine learning problems? No. So thank you.
Right. So the core of the question is whether Kaggle is a good proxy for machine learning performance.
Sorry, can you say that again? I missed that.
Whether Kaggle and datasets on Kaggle or competitions on Kaggle are a good proxy for performance of models in specific tasks.
Probably not the best person to answer this, but I think it's a benchmark as many others. So I think it's a good one, but maybe, yeah.
Yeah. So I feel like all models are wrong, but some of them are useful, right? So it's definitely useful. Right? Either it's a good proxy, but I think we need something better.
Great. I hope this answered your question. Great. So let's conclude with a topic or an area or something specific that you have in mind that you're excited about in the next, let's say, year to come on your area of research or action. Yeah. Whoever wants to go first.
So maybe I can start. So I think so I think one of the things, I mean, coming from hardware and systems, one of the things I'm very excited about, I think, is so I think there's a couple of things. So one is this landscape of emerging systems. I briefly talked about it in my talk, right? I am certainly very excited with all of the new ways of building systems, right? Like all the way from very advanced packaging. So a lot of technology based, right? But advanced packaging to build, chiplets and connect them on wafers and connecting these things up with photonics. I think there's a lot of exciting technologies. These are technologies that have existed for a while. And again, that same argument, the economics of AI and ML has made them, quite promising and mainstream. So I'm certainly looking to, what that allows us to do and enables. I think one of the values that hardware and systems has brought to the ML community is just enabling things that were not possible earlier, right? So larger memories, pools of memories, like easier to communicate, just means that we can potentially run and train larger things. Whether or not that's the end model that we'll deploy, at least it opens up research opportunity. I think that's something I'm excited about. And I think personally, I also mentioned this. I've just been following this space about, on these RAG-based techniques, and I'm just very curious whether it is going to be yet another just passing phase, or this becomes something that we'll talk about in this panel next year, right? I'm just very curious to see how that pans out. Yeah, thanks.
Yeah, so I think one thing that I'm really excited about, I think this will be the year that we understand more about data quality to model quality. Yeah, so essentially, if you want a model have certain behavior, what data should you put in? If you want to build the next state-of-the-art model, how can we just shrink the internet into this high-quality core that many people can train it? So there are definitely this different successful story from different companies, but I think this will be the year that the community figure out, right? So I think, so that's really exciting from my perspective. Yeah.
Great, thank you. Dan?
I mean, I guess sort of our next goal for the for the following, let's say, 12 months is kind of to investigate extreme levels of compression. So essentially, can we go close to a bit or even below 1 bit for popular models that people are kind of working with? So I think that opens up. That opens up a lot of challenges on sort of the accurate compression side, but also with respect to coding and a lot of kind of hardware-aware software design. So I think those I find very, very interesting, and yeah, sort of it has very nice connections to areas that like coding and that sort of thing.
Great. Then I would like to thank everybody for participating in this panel session and in this workshop. Let's give a round of applause to the speakers. And looking forward to seeing the next big thing out of each one's labs. All right, thanks everybody.
Thank you.